Good day. Our topic for today is about closed sets. Now, when can we say that the given set is closed or not? Let me discuss first the concept of complement. Now, we let A be any given set. So we have here A be any given set. Then the complement of A is equal to this set okay. So this is the symbol for the complement, and then it is the set of the elements of R wherein X is not in the set A. So if we use the Venn diagram, we can illustrate the complement of the set A. Yes, say for example this is our set A, so the complement is outside A. Okay, this is the complement of A. Now let's have an example of the set. Say we let A be equal to this set, this interval. Of course, the complement of A is equal to this. Closed in 2, then union, open in 5 rather. So open in 5, then positive infinity. So this is our complement of the given set. Also recall that A is open if and only if it contains all of its interior points. So we can now define closed set in terms of complement and open set. So we have here the definition of closed set. A subset A of R is closed if its complement, we have here the notation, is an open set. Now let's try to consider an example. Say let's have A be equal to this set, this one. Okay. So of course the complement of this set is this set, then open in -1, union open in 3 to positive infinity. Now notice here that this interval is open, so with this interval, and we know that the union of open sets is open. Therefore, the whole thing of this is open. Hence, we can say that the complement of A is open. Now, by using the definition, if the complement of the set is open, then we can say that the given set is closed. So we can say that A is closed. Note that in our previous example, say we have this one. Let's have here another example using our previous example. We have 2, then the 5. And if we are going to get the complement of this, we have negative infinity, then 2, union, we have 5 with this. And we all know that this interval is not open, right? So we can say that the entire of this is not open. Hence, the complement of A is also not open. So we cannot conclude that A is closed because its complement is not open. So we can say that A is not closed in this case. So in general, any set, in general, any set that has this form AB, as discussed a while ago, is closed, where A, B are real numbers. So in general, this form of set is closed. Now, we have a question. Is an empty set closed? Is this closed? Is that closed? Okay, let's try to answer this one. First, we will get its complement. Now, what is the complement of an empty set? So, an empty set, the complement is, of course, the set of real numbers. Because we will consider our universal set as the set of real numbers. Therefore, the complement of empty is the set of real numbers. In our previous discussion about open set, we conclude that the set of real numbers is open. Hence, we can say that its complement, the complement of an empty set, is open. So by using the definition of the complement of a set, if the complement of the given set is open, therefore the set itself is closed. Right? So what about the set of real numbers? What about the set of real numbers? Okay. Is R closed? So, is the set of real number closed? Okay, let's try to get its complement. So the complement of R is, of course, the complement of the universal set is an empty set. And we have shown this before, that an empty set is an open set, right? In our previous discussion about open set, we have shown that an empty set is an open set. It means it is vacuously true. There is nothing to argue that an open set is that an empty set is an open set. So since the complement of R is open, we can say, by using the definition of closed set, we can say that R is also closed. Hence, empty set and R are both, as you observe, they are both open and closed sets. So we have here our remark that the empty set and the set of real numbers are both open and closed sets. Now we can also define open set in terms, closed set in terms of its accumulation points. So we have this one, the theorem. It states that a subset A of real numbers is closed even only if A contains each of its points of the accumulation. Points of accumulation. So in other words, or shall we have this symbol, A is closed. So A is closed if and only if it contains all of its accumulation points. So it means the derived set of A is contained in the set A. Note that if we have this notation here, this means subset or equal. In other book, they use this one as the notation for subset or equal, the same. So in our discussion, we use this one as our notation for subset or equal. Okay? So let us try to consider example here. Okay, for example, let us have A be equal to this one. And of course, in our previous discussion on the accumulation points, the derived set of this is equal to itself, right? This one. Now notice that the derived set is equal to the set itself, and hence this set contains all of its accumulation points. So we can say that A is closed in that case. So that's all about closed sets.